Hello, everyone. This is John Avina from Abraxas. I'm here with three guys from Bernhard. So what I'm going to do is I'm going to introduce in a very vague way who these people are, because I've never met Jaron, Greg, or Jim before, but they will tell you who they are. But I read their paper and it was kick-ass. So they put a paper out in the International Journal of Energy Management, and I think it was in the last 12 months, and I voted for it to be I'm on the board, so we all get to vote on which is the paper of the year, but that was my vote for paper of the year, was your paper. It was the best of all the articles that I read. I read them all. Anyway, what I found amazing was this is, it's a novel approach. This is a different approach to chiller efficiency I've never seen before. At least maybe among facility folks it's not novel, but among energy engineers we don't think this way. It's really, really amazing. And I guess that will be my introduction. So why don't you guys introduce yourself and then show us what you know. And you guys, people in the audience, you can ask questions and we will answer them at the end. Okay. So yeah, let's go. Let's see what happens.
All right, thanks, John. So as you can see on the screen, I'm Jim Crockett, and Greg and Jaron, the three of us worked on this project, and I'll introduce Greg and Jaron in context in just a second. So what got us started on this chiller project or study, I guess, is we had a client in Puerto Rico who had a large chiller plant. So over the course of a calendar year, this plant in Puerto Rico averaged about 800 to 1,000 tons continuously all year long. And electricity in Puerto Rico costs about 25 cents a kilowatt hour. So this one plant was spending over $1 million a year just in the chiller plant. This is about a 200,000 square foot building, so it's not even all that big. And given the amount that they were spending on their chiller plant, any drift in efficiency was going to have some real monetary implications. And we knew that we could fix their plant, but what we didn't know was if we were going to have to go back the next year and fix it again. And thinking about it, we realized we didn't know how often chillers failed or how often things went wrong with them. But we did have the ability to answer that question. And here's what I mean by that. We have a large healthcare client in Arizona where we're monitoring 30 plus hospitals, and we have 78 chillers across this healthcare chain. And we have analytics installed on the chillers. I'll get into that in a minute. And Jaron's role in this process is he goes in monthly and looks at the data that's being reported back by the chillers. And he identifies if there's an issue with the chillers, if the efficiency has changed or if something is different. And if that's the case, he notifies the customer, and they go in and they make the changes as needed to fix it and restore it back to correct operation. If needed, he'll rope in Greg Jimmie, and Greg Jimmie has a knack for understanding how chillers work, and he's just unusually good at identifying the root cause of chiller problems. And so that's his role. He's extraordinarily good with chillers. Jaron Peck is very good in his role of identifying issues as reported and coordinating that with the client, making that work. So what we did is we decided to go through the data that we had gathered over 3 years from these 78 chillers to see what we could learn. Some of the stuff that we're going to talk about today, one of them is the results of what we found, and Jaron's going to take care of that. Also, examples of what sort of chiller issues we're detecting, and Greg's going to spend some time on that. In preparation for this presentation, we realized that maybe the article that we presented from 2019 to 2021, we found a lot of problems with chillers, and we thought maybe we had a Chicken Little moment where we had announced the sky was falling and things looked worse and so on. So we were a little nervous when we went back and pulled 2 additional years of data, 2022 and 2023, And so Jaron will talk about what we found when we went back for the, for the sequel, find out what happened next. And then at the end, we'll have time for questions. So to revisit, here's what our questions were. Ultimately, we wanted to find out how dependable are chillers in general. How commonly do they fail? How frequently do they fail? Which failures are most common? What's the cost of not doing anything? So if you just let your chillers run, as most people do, for 10 or 20 years, how much energy penalty do you likely accumulate? And related to that is, when chiller failures happen, is it the same failures happening again and again, or is it new failures popping up each time? The reason that matters is because as Jaron reports the issue to the client and they fix it, if there's another chiller error a year later, is it the same one repeating? Because if it is, then you don't really get an accumulation of errors effect. But if it's new problems each time, then letting it go for 10 or 20 years can, you can accumulate a lot of issues. Very briefly, the reason we were looking at chillers is chillers are the biggest energy consumer in most commercial buildings. If you look at your typical electric bill, 30% of the energy on that bill probably went to the chiller. 30% or more, depending on where you're at, what time of the year it is. Maybe in the winter it's less. And most people buy a chiller, install it, and then expect it to run for 20 or 30 years. They'll do preventative maintenance on it, but that's about it. And when energy auditors come through, they rarely look beyond set points. Well, is the chill water temperature too low? Could we bump it up higher? Could we reset it? Same thing with condenser water, but they don't look beyond that because it's packaged. And so I had some conversations. I've got a friend / mentor out of the Dallas area. His name's Paul Esom, and he works for Palmetto Test and Balance. Hope I got the name of the firm right. Anyway, I was talking to him about air handlers, which are similar. They come as a packaged system, and his company for the last several years has been testing brand new air handlers as they arrive from one of his large clients. These are 50,000 CFM air handlers and higher, and they do leakage and deflection testing on these brand new units. And what he told me is 30% of them arrive on site already defective. There's something already wrong with them. And if it's a buildup air handler, it's even higher. It's like maybe 50, 60%. But you don't ever hear about that. And the inability to see what's going on into chillers or to the failure to commission air handlers has led to manufacturers not being held accountable. You don't know if you're getting a good chiller. You don't know if you're getting a bad chiller. So that goes back to the question. So how dependable really are chillers? Now, if chillers are failing, why don't the building owners notice? Well, the answer is sometimes they do notice. How often have you been in a chiller plant and you're talking to the operator, and the operator says, well, we've got chiller A and chiller B, but chiller B has got a bit of a different personality. If you have two chillers and they're the same chiller and they're not running the same, it's not because of a personality, it's because something broke in one of the chillers. But they don't know what to look for. Now, another reason that the building owners don't notice is generally these failures are not catastrophic. In other words, they don't shut the chiller down. They just don't perform as well as they did. So of the 109 problems that we observed during the 3-year period, none of them was fatal, causing the chiller to stop. They just continued running, wasting energy. About the study itself. So we looked at 78 chillers from 2019 to 2021. We monitored the refrigeration cycle. And Greg will give a more detailed list toward the end, but we were looking at temperatures, pressures, and power. Those are the main 3 things that we're looking at. And if you measure those in the right place, that allows you to essentially see what the refrigeration cycle is doing. And if it's doing something that it shouldn't, it allows you to call it out. Now, I should also point out that these chillers are not neglected. We've got a good client. They're doing their preventative maintenance. They're responding when issues are found. So the error data that we're going to present is from machines that are really pretty well maintained. So between 2019 and 2021, we found 109 new issues on this fleet of 78 chillers. At that rate, so if you take 109 issues, divide it by 3 to find out how many issues you had per year, and divide that by 78, you find out that there was roughly a 47% chance of a chiller developing a new energy wasting problem during any calendar year. Now, if you have a fleet of chillers, you notice this sort of thing. If you have one chiller, what will happen is you'll have a year go by where nothing happens, and then you'll have a failure every other year. You'll have 2 and 1. You know, it's a mix. It's not until you're looking at a large group that you can actually detect a pattern and distinguish that from you just having a wonky chiller. One of the questions that came up, so we had 109 issues, but is this an 80-20 case, where 80% of the problems come from 20% of the chillers? And the short answer is no. There were a handful of lemons, like we had one chiller that had 7 problems, one that had 5, one that had 4, but there were 33 chillers that had more than one. We had 26 that had 1, and only 19 out of 78 chillers didn't develop a new problem. What that means is if you have a chiller and 3 years go by, there's about a, whatever that number comes to, 70 to 80% chance that something has probably gone wrong with your chiller, and possibly more than one thing. One important detail is, were the problems that occurred new or were they recurring? And the reason that matters is because if each of these problems that pops up is new, then it means that after 10 years, you have a chiller that's accumulated, a half dozen problems. Whereas if they're recurring, well, you have a chiller that, whether you're year 1 or year 10, it's only got one problem. So, and what we found is that most of the problems were new. Out of the 33 chillers that had multiple problems, there were only 12 instances where the same problem happened more than once. So generally, when chillers experience new problems, it's new problems. So if you're not staying on top of fixing your chiller problems as they arrive, and you're probably not, because you probably don't have a way to detect when things go wrong. If you're not detecting what's going wrong, you're going to be accumulating new problems. One other really important thing that we found from this, and from the work that Jaron's been doing for for our client, is that chiller performance doesn't get worse because of wear, so to speak. If you look at it, it doesn't just gradually drift and get worse over time. There's discrete step changes in performance that happen. So the reason it's running worse after 20 years is not because it just gradually wore out. It's because there were several discrete energy saving or energy penalizing issues that happened that weren't fixed. When Jaron finds them and reports them, the chiller goes back to its regular efficiency. And that was kind of a big find. And now I'm going to pass it over to Jaron and let him talk about what it was that he found.
All right. So using the data for each chiller that we had available, we were able to identify whether or not that chiller had a energy efficiency impacting issue or not. Over the course of our analysis, we found some issues that were more common than others. And the graph here shows the breakdown of the issues that we found and how frequently they occurred. So you can see that the most frequent issues that we ran into over the 3-year period were, first of all, these IGV issues. So IGV, inlet guide vanes, or some chillers had what are called variable geometry diffusers, which are a little different from IGVs, but we lump them into the same category. But we would see sometimes IGVs backing off to control load at times when the compressor hadn't yet reached a minimum, or that the IGVs just in general were just backed off all the time. And that can happen if the surge map had been so filled out that the chiller essentially just, so to speak, painted itself into a corner in its operating conditions. So then, yeah, the second most frequent was low refrigerant charge. So over time, especially if a chiller is like a positive pressure machine, the refrigerant can slowly leak out of it, and it has to be periodically refilled. Using the data, we can see when this has passed a critical point where the chiller efficiency is greatly impacted by the lack of refrigerant, and that's where we would recommend it be recharged. Staging issue came next at 13%. We monitored to see if the staging, like if the stage points of the chiller plant needed to be tweaked or adjusted just to prevent chillers from cycling on and off. Or sometimes we would see multiple chillers running where the plant could reasonably get away with running less chillers. So for example, sometimes we'd see 2 chillers running when you could easily get away with just 1, stuff like that. Cooling towers, although this wasn't really the focus of our analysis, it was mostly just looking at chillers. They did come into play. They did tend to crop up in relation to our chiller analysis, so that's why it's on the list. But mostly in relation to, like, high approaches, staging, or other sequence issues with the cooling towers. Flow control was next at 11%. So this is like whether or not the flows were meeting set point, or if the flows were below like a minimum set point, which may cause the chiller to surge if it's not getting enough flow. In some cases, we found that flow was taken by one chiller from other chillers, so it was essentially robbing flow, putting those other chillers in danger of surging as well. Fouled condenser tubes, 10%. Usually condenser tubes will get gunked up over time, but are usually cleaned annually. They'll usually get brushed every year. But sometimes we find that the condenser tubes get gunked up pretty early, especially if the water quality in the area is low, in which case it may need to be cleaned out more than once a year to maintain chiller efficiency. The last one I want to talk about, we had some kind of more minor ones, but were just bad sensors, especially if the chiller is controlling to one of these sensors. It may cause it to run not as it was originally intended. Like if there's a chiller water leaving temp sensor that was bad, it might be controlling the vats and ramping up the chiller to maintain a temperature it'll never get. So those were probably the most frequent that we ran into through this analysis. So go to the next slide. Let's see how expensive were these problems. So on this table, you can see this is the average yearly penalty per chiller. So the annual penalty per chiller for each of these issues that we identified. So if, say, one of these issues goes unidentified, this is the amount it could be costing per year per issue here. So some of these top issues that have the highest costs are some that you saw on the previous slide. So like staging issues is pretty up there, cooling tower issues, sensor issues, and IGBs. We did have one issue that was pretty unique. It was a bypass control issue where when all the chillers were running full load, the bypass would occasionally open, causing the return temp to go down, which in turn caused the evap temperature to go down and pretty much made the load spike, and all the chillers were surging. So just some of the things we've ran into. But these costs here, they will vary by the chiller size. This is just the average that we came across. Kind of our next step would be to kind of normalize all these by load so that we can see what the cost is per load on the chiller. It's just to get a more accurate representation of the true impact of these issues. So yeah, up next, Jim's going to talk about the accumulated energy impacts.
Okay, thanks, Jaron. And so what we're seeing on the graph here is and again, this is portfolio wide, it's the cumulative monthly penalty. You know, if the customer were not to fix the errors as they arrive, this is the extra spend they would be spending each month. So after 40 months, for example, they'd be spending an extra $40,000 a month, which is a lot. So but what is that? How much are we talking about? So on the next slide, kind of have, if you're looking for a number to hang your hat on average, it's about your chiller fleet will degrade by about 2.5% per year. That's if you have a fleet. If you have an individual chiller, it'll probably hold steady for 4 years, and then you'll have a 10% hit 1 year. But the average is about 2.5% per year. And the blue shows what the annual penalty is. The orange indicates how much have you spent extra to date at each of these points, and that recognizes that only 65% of the issues are going to be compounding, 35% are going to be repeat, et cetera. But anyway, if you're looking for a high level number of what it costs you to not fix chiller problems or to not detect and fix chiller problems as they occur, your plant will get worse by, on average, about 2.5%, get worse by 2.5% a year, roughly. All right, now I'm going to pass it over to Greg, and he's going to talk about, we talked about what we found and what we identified. He's going to show what that looks like. What things are we watching? What is it that we find? What is it that we do, et cetera? So Greg, I'm passing it to you.
Awesome, thanks, Jim. Yeah, so basically kind of just wanted to get into what does the data look like and give you some stories behind the data as we were finding issues and then getting them resolved. So but this first example is we were talking about 2 twin chillers. So what that means is it's identical chillers. They're same capacity, same manufacturer date, sitting in a plant and exhibiting pretty different behavior. This was something that we were noticing, that the discharge superheat on one of these machines, chiller 2, so the red line there, operating significantly hotter than the other machine, its sister counterpart. And when we were going back to the manufacturer about this, they kind of repeatedly dismissed it and were like, hey, well, it's within tolerance of where this machine can run, so we're not overly concerned about it. And if anything, it's going to be, we would attribute this difference in performance to a flow imbalance. And we never really loved that answer, so we kept prodding and prodding. Eventually, we were able to coordinate with the controls vendor and the chiller manufacturer on site and kind of like flesh this out together as a group effort. So first thing we did was address that flow issue or that flow concern, and we got the 2 chillers to operate, within 5% of their flow of one another, and we were still seeing the problem. And so it was like, okay, so we all agree it's not a flow problem. What else could it be? So the chiller tech started to essentially manually manipulate how the chiller was loading up or unloading. And we kind of got caught by surprise that as he was trying to load it up, the chiller actually unloaded and tripped on a low evap temperature or low evap pressure. And so it kind of was like, that wasn't what we expected. What's going on here? And so we started to look into a little bit more of what was the physical happenings going on. So we noted that the variable geometry diffuser actuator seemed to be doing the opposite of what he was commanding the chiller. So as he was trying to load it up, it was sort of throttling things back, and it didn't look right. And then comparing it to its sister counterpart, we were noticing that they were in different positions, even though they said they were at the same percent open on the IGB. So I basically noted that one actuator on chiller 2 looked like it had been new. It was slightly different paint, or paint was scuffed off in a way that we were like, this looks like it's been serviced and serviced incorrectly. So kind of pointed that out to the chiller tech, and he was like, no, you're right, that actually looks wrong. So we got the approval from the facility owner, or the building owner, and we shut the chiller down, reoriented the shaft on the actuator, and fired the chiller back up. And it was this really kind of like aha, like proof in the performance. As soon as we fired it back up, the kW per ton went down. And if you go to the next slide, you can see that the discharge superheat and the efficiency on these machines, it's almost the same graph. So you can see that once we fired it back up, it was as good, or even maybe arguably slightly better than its counterpart. So it was just this really cool moment of us sort of working together and correcting the problem and sort of that line in the sand of before and after, and significantly improved performance. So that was a really cool one, and it really shows the idea of like seeing like for like chillers, and one of them is not quite the same. The next one I think was a similar issue. It was actually just on the flip side. So instead of inlet guide vanes, it was instead of variable geometry diffusers or VGDs, it was the inlet guide vanes. But same sort of thing. This one was sort of backed off all the time. It was impacting its performance, and we noted that essentially just needed to be reset. It had lost its position, if you will. And so same sort of story occurred here. We don't have quite that clear line in the sand, but this first graph sort of shows you that, you know, you're operating maybe 15 or 20% worse efficiency when the two chillers are operating together. The next graph will kind of show that unfortunately not running together anymore, but as they switched over from one to the other, their performance was almost identical. You know, within the same week, you know, approximately the same, you know, average kW per ton. So similar sort of story behind that, twin chillers, and they're just exhibiting pretty different behavior, particularly when we're looking at their efficiencies. The next slide would kind of jump into one of the more popular, let's say, more common findings that we came across was low refrigerant. I think that this is something that most building owners are aware of, a thing that can happen. But what caught us by surprise was how frequently, the high clip rate of it occurring. And so this was one where you can see these two graphs in the bottom, essentially baseline and retrofit. It's really kind of maybe confusing, but it's like, this is your baseline data of how the chiller was performing, and then over time, you know, what are you comparing it to itself? So this is actually kind of funny that, so chillers 1, 2, and 3 are the same chiller type. 3, 4, and 5 at this plant are the same type. So this is one of those prime examples of the facility just attributed chiller 1 as having a personality, particularly when compared to chiller 3. And so as we dove into the data and gathered more data, it painted this picture pretty clearly that this chiller was actually just low on refrigerant. And we had the data to sort of prove it to the chiller manufacturer of saying, like, hey, baseline, this was operating with about a 2-degree evaporator approach. It's now up close to 8. And then similarly is on the suction superheat, it was essentially operating at around a degree or 2, and then same sort of thing. It's kind of crept its way up to about 7 or 8 degrees. So it kind of got to the point where this was undeniable for them, and they were able to get out there and charge that chiller and then see it fall back in line with sort of chiller 3 and its ability or its performance. So kind of this that chillers don't have the personality. There's usually something wrong. You're just not looking in the right places. So that's low refrigerant. Typically, we can see that on the evap side. The next slide kind of points out that we'll see fouling tubes on the condensing water side. So this is just a similar sort of thing, comparing a chiller to itself over, you know, basically a year, and you can just see how much that's degraded. The interesting story about this site was it's a local Phoenix site, and the water quality here is not exactly great. And so what they ended up opting to do here in this case is, because we kept repeatedly finding this issue, even with their annual service, that they essentially changed their service contract to be punching those condensing water tubes twice a year. The financials for them worked out where it made more sense to do that between the water quality treatment, or the water treatment, water quality, and that additional service. It made more sense for them. This site also had plenty of plant redundancy. So, you know, rolling a chiller off for a week or a few days at a time didn't really sacrifice, even if they had to do another service in the middle of the summer. So that was a unique sort of solution for them, not necessarily a one-size-fits-all. But I think what this sort of points to is that by looking at the data, you can sort of cater your servicing contracts or service provider to say, hey, I need to look at these specific things when you're out here next, or hey, I need you to go do, you know, chiller tubes more frequently, or, you know, in some cases maybe you can extend it and do it every 1.5 years or every 2 years. So kind of it lets you cater your service based on what the data is telling you. So the next slide is kind of a unique one in the sense that we developed sort of a custom in-house surge analytics. And we did this in tandem working with a mechanical vendor that services these chillers. Particularly something that they were concerned about, because they have a contract that they service all this entire fleet. Many of the chillers are 20 years old, so, you know, catastrophic failure is very much on their radar of something that they want to do all they can to prevent. And so monitoring surge became sort of this like high priority thing for us to figure out a way to track. And so what this is a depiction of is a site where they had essentially turned the chiller to operate outside of its design condition. So typical design selection in Arizona is like 42-degree chilled water leaving, and then 85, 95 on the condensing water side. So coming into June and July, we're actually hitting some of those design sort of days. And what happened at this site was also during that same sort of time of the year, we start to get some humid weather creep in as well. So what they were trying to do was make the colder chilled water to combat the humidification, or rather dehumidification need in the spaces. And so what they did was they lowered the chilled water temperature minimum down. We historically were able to get by with 44 at this site, even though it was designed for 42, but they dropped it down to 40. You can kind of see that step change there towards the end of June, which is sort of the first half of that graph. And then the second half, that circled area in red, is where it was regularly hitting that new low limit on the reset. Essentially now this is operating with 40-degree water leaving and 95-degree water leaving on the condensing water side, which is too much lift, too much load on that machine essentially for what it was designed to be able to do. And so within that red box, you can basically correspond most of the time where it's hitting that 40-degree temperature. Sure, it's hitting it, but it doesn't like being there, and it's causing these surge events pretty regularly at the time. So it just became this really important thing and good metric for us to be able to get back to the facility to say, hey, we've got to figure out a different solution for your dehumidification needs, because we're potentially putting these chillers at risk, especially as we roll into July and August, where loads are pretty high. And in this case, they didn't have as much redundancy at the site. I think they had one extra chiller, but that was it. So if you lose one, now you don't have that redundancy. And it was just this sort of like the data pointing us to like having to push towards a new solution, and working with the facilities to help find that solution. The next one kind of points on another really common issue, is the inlet guide vanes, or these IGV issues. So this is a great depiction of it, particularly that lower graph, the middle one. Between the blue and the red line, you can see that those are operating pretty differently. The red line is chiller 3 in this case, but it's typically backed off all the time. So it rarely opens up more than say 40%. And that corresponds to just basically an unnecessary pressure drop across the compressor. So that generally lends itself to showing a high discharge refrigerant temperature or discharge superheat. Whereas the other chiller was able to modulate those much more open, more regularly. And so its discharge temperature generally ran cooler by comparison. The lowest bottom graph is a little bit harder to see, but the top, the red line is essentially pegged at 60 hertz all the time. So what that tells us is it's doing all of its modulation for capacity variation with the inlet guide vanes, rather than taking advantage of the VFD and modulating the compressor speed. So it essentially takes that VFD out of the picture, and its efficiency and ability to modulate that way, save energy that way, is gone. Whereas the other machine was able to modulate, it was regularly hitting say 50 hertz while the inlet guide vanes are backing off. So that's generally what we like to see. The solutions on that typically ranges between resetting a surge map, is do it with caution, I guess I will say. Typically, we only make that recommendation if we make significant changes to the sequencing in that plant. So essentially, the chiller can sort of relearn what new normal operating conditions are for it. The other one is that on these IGVs, it's not a true position known from the actuator or from the potentiometer. Essentially needs to be reset or re-zeroed from time to time. So that was that other issue. It was essentially lost. Where it thought was at 100%, it was probably actually closer to 50 or 60% open. So that's another one that's not super known, but as our data points out, this is a pretty common issue that should be kind of on people's radar that generally would be missed, I guess you could say. And then the last slide is kind of just a couple other examples, a couple other things that we will just generally see. I think some of these are more particularly related to air-cooled chillers. So like when we're seeing a big step up in the high side pressure or the high side superheat, You can say that would be like a worn bearing or a bearing that's failing. That's a big one to catch early because a compressor repair is generally significantly cheaper than a compressor replacement. So monitoring that is a good thing to kind of like catch that before it's too late, before you hit that catastrophic failure. The other one that we see is the non-condensables or air getting into the system. This is typically on those negative pressure machines. So Jaron kind of indicated that more common issue on positive pressure machines is where they lose refrigerant. So, you know, any crack in an O-ring or anything that didn't quite get tightened down enough will lend itself to leak the refrigerant because it's positive to atmosphere. On the negative pressure machines, they're negative to atmosphere, so they'll generally tend to bring on air. And so what we'll see on those is that will essentially act as a barrier for the heat transfer. So you either need to get the air out, particularly you'll have like your purge units that aren't working correctly. The purge units can also leak refrigerant as well, but usually it's they're not functioning and getting the air out of the system correctly. And then the last bullet there, kind of just I think just a general note for everybody, just be keeping tabs on what's normal for your chillers when you're looking at the evaporator and condenser approach temperatures. It's like almost always available. It's a good metrics to start with that you can start pointing out some of those bigger issues of, you know, fouling tubes and low refrigerant. Pass this back to Jaron and he'll kind of break down, you know, what is some of the new findings or the new data set telling us.
All right. So as Jim was saying in preparation for this webinar, we wanted to take another look at this project to see how things were going since our initial analysis that took place between 2019 and 2021. Also, as Jim was saying, that the clients, since they have been really diligent in making repairs, keeping up on their preventative maintenance, we were kind of worried that we kind of maybe just did our once through. We found all the things, fixed it. In the first 3 years since this whole monitoring project started in 2019, and that issue identification would slow down over the next 2 years. So yeah, we wanted to see if that would happen in just kind of afterwards, going from 2022 to 2023. So this is what we found. So in the year, our first analysis in 2019 to 2021, we found that there were 109 total issues across 78 chillers. So that corresponded to a 47% chance that a chiller would develop an efficiency impacting issue over the course of a year. Looking again at our 2022 to 2023 data, we identified 111 errors, or 71, which increased that to a 71% chance of a chiller developing an issue over the year. So this was surprising. There may have been a few reasons for this increase. One being that as chillers age, or the more that we look at them, the more likely they are to develop an issue. It could also be that since we started, we had refined our process a bit more, and I think that probably had some impact as well. But what this does highlight is the importance of continuous monitoring, being able to catch these things periodically as they come and fixing them. Will keep energy costs down, chillers will run more efficiently, and ultimately probably extend the life of the chillers as well. So if we go on to the next slide, we'll see a comparison of the issues that we found for each of those analyses. So on the left, we have a compilation of the issues that we found in the first 3 years, 2019 to 2021. And then on the right, the issues from 2022 to 2023. Some things to note is that the frequency of some of these issues increased. Namely, you'll see in blue there, the low refrigerant issues went up, as well as some of the staging issues. Cooling tower issues also increased, as well as chilled water set point issues in kind of that brown color. I hadn't really talked about those, but that is mostly looking to see if chillers are meeting their set points, or if like the set point isn't reacting properly, if it's not resetting, stuff like that. So yeah, it kind of varies what kind of problems the chillers are going to develop. It just also again highlights the importance of just a more in-depth chiller monitoring plan. And also, we have seen that even if there are small issues that go unidentified for a long time, they can have a really large energy impact if not addressed. So yeah, just the importance of constantly looking at these things and finding and fixing issues. I'll hand it back to Greg, and he will talk about what's actually needed for chiller monitoring.
Yeah, so basically what do we need? I think the next slide shows a little bit more, but I'll stay on this one for a moment, is that the two main hurdles that we have is that the chillers may be old enough that they just don't monitor everything, or they're not readily available, particularly like, they don't have a BACnet card, for example. And it's kind of mind-blowing to me that chillers in our modern era, Internet of Things, AI, whatever, and chillers still get ordered without comm cards. So start there. At the very least, get your chiller to communicate the data, because some data is better than no data. We can't track what we can't monitor, and so I think that's a big one. If it's an older chiller, a lot of the times you can add the external sensors or add a power meter if it makes sense. If you don't have a plan or a roadmap to replace those chillers, that's usually a feasible thing to monitor some of the basic stuff, and the refrigeration cycle and all that. Power meters is a big one on that one, particularly those older chillers. Some of them that's not available, so getting that extra power meter. The other one is just the lack of availability of the additional points. So some of the data will be readily available from those comm cards, but a couple major points may not be. Depending on if you get that, you may have sort of extra layer of analysis available to you, but sometimes it's not necessary to get like the big picture things. So I think just the big takeaway is making sure that you're getting some data gathered and collected from your chillers. Otherwise it gets really old school really fast. If you have guys just taking notes every hour in a clipboard, we can use that, but it makes the whole process to do analysis on these chillers a lot more difficult. So the next slide kind of gets into what are the actual points, the major points that we're looking at. Those first two or four technically are condensing water entering and leaving, chilled water entering and leaving. Those should sort of be no-brainers. I assume most everybody's tracking that, whether it's from the chiller or from their own sensors in their control system. The compressor discharge temperature, that's pretty common on water-cooled machines. Usually is readily available. The high side pressure and low side pressure, so evap and condenser pressures, that kind of will correspond to a saturation temperature of the refrigerant. That's sort of key to be monitoring those approach temperatures. So your saturation versus the leaving water temperature. This is just sort of a good one to have on your radar to start keeping a tab on it, just what's normal for those chillers. And if you see it deviate, it can happen quickly or it can happen sort of over a month or two. But just sort of knowing where you start is worth having that one sort of on your radar. The suction temperature on the compressor inlet, so that one's typically not available. So that is one that we'll add an external sensor on and monitor that way. That one we find is a better metric in tandem with the evaporator saturation and whatever approach temperatures is a really good sort of supporting data point, that suction superheat, for identifying low refrigerant. The DP across the evaporator and condenser barrels, that one's good. If you don't have flow, it's a good sort of proxy for flow. We won't get all into how flow is measured and all that in this discussion, but it's worth having in there. Sort of the same sort of thing of identifying if your DP deviates over time. The temperature at the expansion valve, that one's kind of like 50-50, I would say. We have that added on. Sometimes it's from the factory, sometimes we'll have that external third-party sensor added. That's basically to track your subcooling, and another good metric for us to track the chiller's performance. The chiller KW, that one, the biggest caveat there is just understand their chiller quality, the power meter quality. So, we found that some of the manufacturers' power meters were just not as accurate as we would like them to be. So we would put on sort of a third-party higher quality power meter on those. So just something to be aware of and keep an eye out for. Compressor oil temperature, that one, typically is for your traditional sort of ball bearing components, where you'll have an oil cooling system for those to cool the bearings and the lubricant system for the compressors. But even on mag bearings that don't have those traditional bearing setups, they'll still have a cooling system that we'll want to monitor as well for that compressor. So that's kind of like the high level. If you can get everything, this would be sort of our wish list But kind of to reiterate that getting some data is better than nothing, because we can still do a lot of the diagnostics with sort of the stock or the factory data. So I think those are the big points, and I think we kind of want to open it up. Or we got one more slide for contacting us.
Yeah, so just to wrap up, and thank you, Greg and Jaron. If you've got, here's our contact information. If you've got questions about chillers, Greg is about as good a resource as you're going to find. If you have questions about how to do monitoring-based commissioning, what to watch, what to report, you contact your client every day, every month, every year. I mean, anything related to monitoring-based commissioning, Jaron can help you out. I'm happy to talk to you about the article. I'm not as good at chillers as Greg is, or I don't know as much about MVCX as Jaron does, but I'm happy to chat with folks. For me, the biggest takeaway of this study, and that was my role in this, was kind of directing everything and gathering the data and processing it and analyzing the results that Jaron found, is that chillers fail a lot. And most of the failures are insidious, meaning you don't notice them. You have something, your chiller has failed and it's just continuing to smile and push forward, and you don't know that you're paying 10 or 15% extra for some unknown component. Anyway, if you're interested in chiller analytics, just send an email to marketing or to contact Greg, and we can help you figure out if it's something that makes sense for you to do, or not. Going back to the beginning, in the case of our Puerto Rico friends, where they were spending $1 million a year on their chiller plant, that'd be insane not to have some sort of analytics to detect when things go wrong, just because it's so expensive when they do. And that's it. And with that, I'm going to hand it back to John.
Yep, I'm right here. Okay, so we got some questions from some of the folks that have been here. I'm going to ask them. I'm going to ask one of mine first. So I think a rule of thumb in the industry is chillers have a service life of about 20 years or so. I want to know what Greg thinks, or Gregory, what you think, if that's, assuming that you were able to monitor all these things and fix them as they occurred, do you still think that average 20 years is legit, or would it probably extend and be longer? And to what?
I think there's other components that'll come into it that'll make more sense to replace your chillers at that timeline. The biggest one right now that comes to mind is the refrigerants that they're using. So I think that's something to consider, of getting away from those expensive refrigerants. We still work on chillers out here that have R11, R12, so they're still up and running. For what take that into account. So I wouldn't say that 20 years is like, no, take them out of service, get rid of them. There's still a lot of maintenance things that you can do to get them operating to their, or close to their original design efficiency. I think that's kind of the other component of it, that just chillers in general are more efficient. So you're getting back to its best efficiency point. That doesn't necessarily say that it's as good as our modern chillers. So I would say those are sort of other factors that come into account for potentially replacing a chiller. But to just strictly say, hey, your chiller's 20 years old, you need to get it out there and get a new one on, I would not agree with that statement.
Okay, that's good. Okay, here's a question. Why do you still have low refrigerant issues, especially like the last 2 years? I mean, with the scrutiny of the previous years, why would this continue? Is it mechanical contractors that are screwing up? Why would this be?
Jaron, you want to take that one, and I'll maybe add to?
So let me see if I'm getting this right. Why do chillers still have those low refrigerant issues?
In your study, you noticed these refrigerant issues in the first 3 years. Why were there still issues in the last 2 years when everyone knows? I mean, I'm sure all the clients know that's an issue to be watching out for. Why is it still happening?
I mean, that's a good question. Kind of what I was thinking when we were doing this is, I know what we were saying is that since we do mostly look at positive pressure machines, that no matter how much you try, some refrigerant is going to leak out over time. And just kind of over time, it's just going to get lower and lower. I think why it increased the next 2 years is mostly just because I want to say since we started monitoring it, it was, I think we were just catching them kind of as they came. I'm putting that right. Just as time went on, more and more leaked out, and yeah, we just kind of caught it as it was coming, if that makes sense. I don't know if I'm explaining that right.
I think basically we got better at catching it. I think it's part of it.
Okay, good.
Yeah, I kind of mentioned that as well, just refining the process as well. Yeah, getting better at
and it's just a matter of time. The O-rings or the seals, as those chillers get older, they're going to fail.
Right.
So it's just kind of the nature of it. As you get an older and older machine, it's just sort of the nature of it being a positive displacement machine. It's like it's just kind of inevitable. And I think that the data is sort of just like it's that aggregate. These chillers are just 2 to 3 years older than they were, and so those sort of issues continue to crop up.
Okay, I got a question. Is there a link to the article? I don't think it's online. You have to. It's an AEE publication, Association of Energy Engineers, and you can buy the periodical, unfortunately. And so but it was published in the last year. I don't remember which volume or issue, but it was in the last year. That's all I can say. For Josh, if you want to know more about it, why don't you can just email me at webinars@abraxasenergy.com, and I'll see if I can help you. Is it possible to get a copy of this slide deck? You guys, do you mind making that available? Is that okay?
Yeah, I don't mind making it available. I mean, everything in it's pretty much in the article, so it's not I don't mind sharing the slide deck.
This is just a comment which I don't understand, but I think either one of you guys might. It says adaptive learning should be reset when they punch the tubes. Anyone want to comment on that?
I think he's talking about maybe the surge map.
Okay. That's all you.
Yeah, that one's touchy. Typically, that's really only York machines and maybe some McQuay that they have a map that you can modify, let's say. And yeah, depending on who you ask, they'll tell you what the appropriate time is to reset it. The biggest thing, I just didn't want to give the advice to do it too regularly. The biggest thing is the chillers will surge after you reset it. It's essentially relearning. So that's something that sort of freaks people out, that like, you reset my chiller surge map and now it's surging all the time. It's like, well, yeah, it's kind of what it's for. So I think that's just do it like with a purpose behind it. Don't just go, hey, I've got a chiller problem, I'm going to go start with resetting the surge map. So that would be my response to that.
Here's I guess suggestion. I don't know if you're going to do it or want to do it, but what would be really cool is a follow-on article where you start the article with, these are the things we monitor. Now, when you see this, it means this. This is how you fix it. If you see this, it probably means this, or it could mean this, and you can test it this way. This is how you would fix this, and this is how you would fix that. That would be super valuable to a lot of folks in the field, that they'd be able to try to reproduce this. One other comment, this is mine, and that is, if you could find a way to automate this analysis, that would be really cool. It might involve doing AI type stuff, but if you could monitor all these points and then automate it so that it could find a lot of these issues. I mean, it won't be able to fix them, but it could automate, at least, and direct technicians or someone to look a little deeper into, check this out right here. I think this is what the problem is. That might be a cool idea.
So we didn't actually elaborate on that, but we do have analytics. So that actually is kind of helps cater Jaron to look at certain things. So we have some analytics that will bring those bigger issue items, sort of bring them to the surface or rise to the top. So it's not necessarily bombarding the owner. We sort of will filter it out and then parse those things to give them a cost associated with it and prioritize those. So Jaron, I don't know if you want to speak any more to that, but we do have some analytics. I avoid getting into the AI discussions right now. I'll just leave it at that.
Yeah, no, that's good. Okay, the next question. Why do building owners or key stakeholders sometimes neglect chiller maintenance? Is this a case of boiling the frog where gradual deterioration goes unnoticed as long as nothing breaks? Or Sorry, as nothing breaks or there's no huge step change, we just let it go as is.
Well, couple of things. One of them is it's part of it's boiling the frog. They just the changes are gradual and unnoticed. And then another one is just industry wide. Everybody is stretched thin. You know, it's and so if you have a problem that's not sending off alarms or it doesn't raise an obvious red flag, you know, you're going to go take care of something. You're going to respond to Bob in the corner who's complaining that his office is too hot instead of spending time on the chiller. So it's just, I think a lot of it's just people being stretched too thin, to be honest.
I think you're right. What kind of dew point temperature were you seeing in Arizona for that chill water set point issue? Today, Phoenix shows 105 dry bulb and only 55 degree dew point, 19% relative humidity. I'm curious what other strategy they use for dehumidification.
I mean, desiccant wheels is a big one out here that we see a lot. And then otherwise dedicated sort of booster chiller. So you'll have a switchover valve on your chilled water coil or an additional coil that'll allow it to regularly run down to, you know, say 40 degrees when you can keep the rest of the house at 42 or 44. So those are a couple common strategies that we see out here. And I don't have an answer on the dew point, so sorry, I don't know. I don't know on that one off the top of my head.
Please explain a bit more information on the sequencing errors. Is this an internal chiller control issue or external from the BAS? Yeah, maybe it's just people are overriding stuff.
Generally speaking, when you've had chiller programming issues, has it been because somebody in the building automation system tinkered with something? Is it inherent to the chiller itself, or have you been pulled into that level of discussion on it?
Yeah, so short answer, yes to the former. So usually before we start these monitoring programs, we'll go in and do like a recommissioning, or we'll put in a bunch of sequences to like the chiller plant. So that's usually what we look at when we're trying to identify these issues. So yeah, usually it's like operator overrides, changing set point bounds, stuff like that.
That's what I figured. You show an average 2.5% degradation per year without good monitoring and O&M, but what degradation have you seen with good monitoring and O&M? Well, I guess you know that. That would be your last 3 years, right?
The 2.5 was with good monitoring and O&M.
Yeah, that's right. That's right.
So 2.5 is with good monitoring and O&M. Without, I don't know, because we're not monitoring it, but it would be worse.
Yeah, there you go. What software do you find success in portraying this data? Like local BMS, like Siemens Desigo, or software like SkySpark?
There's the one that we use and the one that the client uses and that Jaron uses. We're using SkySpark to feed it in, but that's only part of the story. There's other software as well. Greg, do you want to take a second?
I mean, we're not necessarily married to SkySpark. We do that, I would say, within Banner. That's their preference. They have a SkySpark server, and so all the data essentially gets scraped from the BAS and brought over to another server. So that's the SkySpark. Connect is one that we have sort of built in-house that does a very similar sort of process. And then what's the other one? It starts with a C. I can't remember now.
Copper tree or something?
I don't know. Realistically, most of them can be catered to gather what you need. And then it's just a matter of like how much of that automation process is either built into it or would need to be custom made. But as far as just aggregating the data, it's really kind of, there's a lot of offerings out there. Clockworks was the other one that. So it's basically anything that we can scrape from the BAS and do. So what that does, it sort of offloads the requirements and the processing power within the BAS. Particularly, we work on a lot of like older sites that are outdated control systems and whatnot. So we're cognizant of not overloading those controllers to do the analytics locally. So pulling that data off and doing it as a third-party service is a better solution in our opinion.
Do you have any recommendations as far as a chiller power meter that you typically use, or maybe some base specifications that you would look for?
The top one that comes to mind I've been most experienced with is just like a dent meter. I don't know the exact model number, but it doesn't say utility grade, but it will be something to that sort of effect. You want to, it's, you know, the plus or minus 0.25 or 2.5%, something like that.
Okay.
Rough recommendation.
In regards to extending the life of chillers through these advanced techniques, this question, or this person was curious if you guys quantify the average life cycle savings or years extended on chillers. I guess you can't do that. First off, you haven't done it long enough, right? I mean, you only have 5 years here, so you don't know how much you've extended any lives, right? Any service lives.
Right, and what we don't know, and what we would the type of data we would hope to have over time is at what point do the compressors start to heat up? See if there's a pattern there. Do they start to heat up after, you know, start to wear after 5 years, 10 years? Short answer, we don't know that yet, but that is something that we're hoping that the data will eventually tell us.
Okay. Do you see these types of issues on new chillers that have just been installed?
Yeah, and in fact, the analytics that we have is something that this client has found super valuable to make sure they get what they paid for, essentially. And so we've absolutely found issues with brand new chillers that got installed, being low on refrigerant, having a problem with the cooling system, whether it was on the VFD or on the compressor itself. We found one where it was double charged with oil, essentially, so it had twice the amount of oil in the system that was really impacting its heat transfer. So yeah, I mean, brand new chillers, absolutely, we find issues on them. And so kind of back to Jim's original question, learning that was a thing with air handlers, you know, we're seeing the same thing on chillers.
Okay. What would be the typical cost to add climate check analysis, initial setup, materials, labor, and ongoing? I don't know what climate check analysis is. I hope you do. Is there a threshold of chiller ton hours per year where it would make sense to provide this climate check thing and monitoring?
That is something that we've looked at, but it's there's too many variables. And what I mean by that, you know, ton hours is one of it, and then cost of power is the other.
Right.
It was just
That's right.
tons of ton hours and tons of, you know, tons of cost. Now, the climate check, that's, Greg may or may not go into it in more detail. What that is that's an API service that we found helpful for making sense of some of the raw data. It's an API to which you can send chiller data, and it helps translate that into efficiencies. For example, you know, you take some of the temperatures and pressures, and it'll tell you, oh, your chiller is X% efficient, or this aspect is 61% efficient, etc. Greg, does that cover it, or is there more you'd want to say?
Yeah, so behind the curtain, climate check is the sort of where all of this data is being processed through. So it's an analytics software that we're essentially gathering some of the data from the chiller, some of the external sensors, and processing it through a climate check software that then is giving us sort of like real-time tonnages, efficiencies, flows. I didn't want to get into that. I kind of mentioned it with the DPs. I don't want to take away from, but the climate check essentially gives you a better lens to be able to do this sort of analytics. And as far as the cost, it's really variable, especially when we're talking about economies of scale. Like, to do one chiller is going to be much more expensive. It might be 15,000, 20,000, like, for a ramp up, depending on where it is. But you know, if you have 50 chillers and you know you do all of them in one go, you might be able to get that cost down to say 5,000. But I'm spitballing numbers. Don't quote me on any of those.
Okay. When adding pressure, temperature sensors on the refrigerant side, have you ever run into issues with voiding the manufacturer's warranty? That's a great question.
Yeah, so that's actually a big one where we want to leverage as many of the factory points as we can. If it's an old enough machine that doesn't have it
Yeah.
already available, then there's probably no warranty to worry about. But yeah, that is something to be aware of. You're potentially creating a point of failure that a leak could occur, and the manufacturer doesn't want to own that. If you're gonna modify the machine that's on you, sort of thing. So yeah, leverage as much of that data from the factory as you can.
Okay, another one. Have we coordinated with IS Delivery to confirm new chillers come with these required points?
I think that's a Bernhard specific question. Let's get offline on that one.
Do you also need points for pumping primary flow, secondary flow, VFD speeds, etc.? And do you need points for the bypass valve? And if the bypass valve doesn't exist, isn't functional, doesn't it need to be installed or replaced?
I think that gets into all the design specifics. When we were digging into this data, we were looking at answering the question of how reliable are chillers. Obviously, as you step back and you want to optimize the plant as a whole, you want to grab those other things. So yeah, VFD powers, frequencies, that's where some of the cooling tower issues that Jaron had mentioned were part of that pie chart of this is an issue that we run across. But to stay focused on what answering the question was here was, we're looking at just the chiller stuff. But yeah, all those other things are valuable as well, especially when you're looking to optimize the plant as a whole.
Okay, another one. Do you have a ROI on the cost of setting up the analytics and ongoing monitoring and subsequent energy savings captured by the program?
I want to jump on that one, and you guys can add to it, but I want to reiterate that analytics don't save anything. As they stand, they don't do anything. You have to have a team that's going to act on them. And I can't stress I can't emphasize that anymore. The analytics alone have no payback. So just making sure that that's very, very clear. You have to have the people that are looking at it and acting on it.
You sound like an engineer.
That exact question is part of what got us on this to begin with. Is what it's one thing to quantify the cost is easy to quantify. How much does it cost to install it? But what's the failure rate? And so the best rough number that we have to work with right now is calculate your total chiller energy and then take a compounding 2.5% per year. And that's kind of work the math. That's a rough number, but that's what we've got at this point.
That's good. Chillers lose refrigerant through mechanical seals no matter what. The low pressure machines lose oil through the purge. I guess that's just a comment. How important are eddy current tests? When do you replace tubes? Are failures usually catastrophic or slow leaks?
The eddy tube, basically, that's to identify if you've got failures within your tubes or you're getting laminar flow. I would say that the recommendation is 3 to 5 years is what I've read. How often we recommend it is essentially never. So if they've got it as part of their standard service, I would say that's when the eddy current testing has occurred. As far as tube rupture and big failures, I have come across that, and it is pretty catastrophic. Essentially, you're way over pumping the condensing water side, and because of the water quality, it essentially etches small holes over time in your barrel. So that's when that occurs, that's a pretty big failure, and you know about it. And so don't overflow your chillers condensing water barrels. That's been something I've really learned from the experience and learning from that at a different site, was that going variable condensing water flow is I'm a huge fan of, and that's a different conversation for a different day. But there's two main camps. People love their constant condensing water flow, and then I'm in the other camp that likes to vary it under specified conditions.
Okay, that's good. Do you find that chiller techs often approach the issues identified with scrutiny and require prodding or working sessions to acknowledge these issues are not being caused by the chill water system flow staging or staging control?
Yes.
Yeah, I think, and Jaron, you could probably speak to this more because you're interacting with the clients more regularly, but I think from my perspective is that it's not a one size fits all. Some clients are going to be very proactive and they want to know the minute something is even slightly out of spec. Other clients are going to be like, well, I want it to be costing me significantly before I act on it. So where that bar is set is sort of a case by case. And even like you might have one overall overarching client, but even one site is a little bit different than the other.
Let me expand that question a little bit. So when we say chiller techs, those can be the in-house chiller techs. And Greg, do you want to take a second and talk about the manufacturer reps? What's your response with them? Are you usually able to? Is there a battle there?
It kind of depends. I think that one of the first examples is what pointed out like a discharge superheat on that chiller of going 30, 35 degrees. And their answer was like, well, as long as it's below 40, we're fine with that. And that wasn't a great answer for us. So that was within their spec is below 40. But is good operation at 35? No. And we sort of had to go through a big process to get them on board to agree that there was a bigger underlying issue. And so like where that tolerance is of, how bad are things before they agree with the analytics or will agree to act on it. It depends on region even, depending on whether you're in Phoenix or California or whatever. So sort of what their history is going to influence some biases, I would say.
Here's a question. I wonder if you made this graph. Did the number of issues correlate to the age of the chiller? That would have been an interesting graph. I mean, this could be a regression or something.
That would have been. I mean, there's a lot of, I wish they'd give us more time to dig into the numbers. And so, for example, find out, does the failure rate vary by age of chiller, by make and model of chiller, by
that too? That'd be
percentage. There's a lot of ways that we would like to go. We just haven't had a chance to do it yet.
Sure. That would be interesting too. This is really, I think, fascinating work you guys are doing. I want you to publish more. Is energy efficiency affected if sensors for the shaft in a mag bearing chiller are bypassed? Does that make sense?
I can't speak. I think I know what he's saying. Like basically the way the mag bearings, they need to be like 100% stable. So I would think that if you're overriding that, you're potentially letting that system get out of alignment, and then once it's out of alignment, you're never getting it back. That would be my concern, but without knowing the exact like application that he's asking about, I'm kind of guessing.
Okay, on those brand new chillers, are most of those issues something the manufacturer can resolve with warranty, or even when the issues are brought to their attention, are they still ducking responsibility?
Within Banner, they've got a good enough relationship with their chiller techs that they're responsive. I can't speak to all. I know that there are definitely owners and manufacturers that butt heads, and you'll get more pushback. I would say the warranties are usually worth getting as a sort of CYA, and eventually you'll get somebody to listen to you, especially as the problem will continue to get worse. Typically, you can sort of have them believe you eventually. But yeah, I can't say for certain. It's usually worthwhile, and you can usually get them, but nothing's 100%.
This is kind of vague too, I think, but maybe not. Does it make sense to diagnose the chiller plant before the end use equipment is fixed? So like an analogy, you have a good heart, but your arteries are all messed up. So does that make sense?
Are they saying, I think maybe like air side is running awry?
Yeah,
and that's driving the plant. Yeah, absolutely. So again, we're kind of like blinders on here, trying to say how reliable are chillers. Again, when we're looking at optimizing a plant as a whole, I mean, absolutely. Your plants should be responding to the end user's demand and modulate accordingly with it. So if you have just pegged out end users, well, you're not going to be able to optimize much of the plant. So yeah, from a whole picture standpoint, absolutely.
Yeah, and expanding on that, we've ignored the topic of load. We haven't looked at are we handling twice the load that we need to. The instrumentation that we're presenting on or talking about today is just how well is the chiller doing what it's being asked to do. Whether it's being asked to do the right things is a very important but separate conversation.
Yeah, I guess so. It's Well, yeah, right. Or if it's running at super low loads or something like that. Do you feel like you're seeing more QC issues since and apparently related to the pandemic and possible reductions in workforce in the manufacturing community as well as the maintenance personnel on site? So I guess, did COVID affect anything and how?
I would just reiterate what Jim said earlier. You know, everybody's spread thin. That didn't do anybody any favors.
Oh, look, we made it to the end of the questions. Look at that. Okay. If I was going to summarize this, maybe you can correct me. If the whole presentation in one sentence or two, it would be that chillers degrade they don't just slowly degrade over time, they degrade in steps as certain little subsections break down. And these little pieces that break or systems that don't function right anymore can be remedied, and you can bring the chiller back to the original efficiency it first had or should have had if it was never working right in the first place. And that chillers need not degrade over time necessarily, or at least a lot less than we're used to. Would that pretty much summarize what you guys have been telling us?
Yeah, I think that's a fair characterization. That's well put.
All right, then. You guys, thanks so much. I'm really, really happy that you guys wrote this paper. I really hope you do another paper showing more information. Not so much, this is what we found the last 2 years, but more like, look, monitor these things. If you see this, do this. If you see this, do this. It would be so useful for the rest of us out here. It would be so useful. You guys, thanks so much. I really appreciate you coming on. Thanks everyone for attending, and we'll see you all next month.
Appreciate it. Thanks.
Thank you.
Thank you.